Chapter 10 of Science and Hypothesis. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Science and Hypothesis by Henri PoincarÄ. Chapter 10. The Theories of Modern Physics. Significance of Physical Theories. The ephemeral nature of scientific theories takes by surprise the man of the world. Their brief period of prosperity ended, he sees them abandoned one after another. He sees ruins piled upon ruins. He predicts that the theories in fashion today will in a short time succumb in their turn, and he concludes that they are absolutely in vain. This is what he calls the bankruptcy of science. His skepticism is superficial. He does not take into account the object of scientific theories and the part they play, or he would understand that the ruins may still be good for something. No theory seemed established on firmer ground than Fresnel's, which attributed light to the movements of the ether. Then, if Maxwell's theory is today preferred, does that mean that Fresnel's work was in vain? No, for Fresnel's object was not to know whether there really is an ether, if it is or is not formed of atoms, if these atoms really move in this way or that. His object was to predict optical phenomena. This Fresnel's theory enables us to do today as well as it did before Maxwell's time. The differential equations are always true. They may be always integrated by the same methods, and the results of this integration still preserve their value. It cannot be said that this is reducing physical theories to simple practical recipes. These equations express relations, and if the equations remain true, it is because the relations preserve their reality. They teach us now, as they did then, that there is such and such a relation between this thing and that, only the something which we then called motion we now call electric current. But these are merely names of the images we substituted for the real objects which nature will hide forever from our eyes. The true relations between these real objects are the only reality we can attain, and the sole condition is that the same relation shall exist between these objects as between the images we are forced to put in their place. If the relations are known to us, what does it matter if we think it convenient to replace one image by another? That a given periodic phenomenon, an electric oscillation, for instance, is really due to the vibration of a given atom, which, behaving like a pendulum, is really displaced in this manner or that. All this is neither certain nor essential. But that there is between the electric oscillation, the movement of the pendulum, and all periodic phenomena, an intimate relationship which corresponds to a profound reality, that this relationship, this similarity, or rather this parallelism, is continued in the details, that it is a consequence of more general principles such as that of the conservation of energy and that of least action, this we may affirm. This is the truth, which will ever remain the same in whatever garb we may see fit to clothe it. Many theories of dispersion have been proposed. The first were imperfect and contained but little truth. Then came that of Helmholtz, and this in its turn was modified in different ways. Its author himself conceived another theory, founded on Maxwell's principles. But the remarkable thing is that all the scientists who followed Helmholtz obtained the same equations, although their starting points were to all appearance widely separated. I venture to say that these theories are all simultaneously true, not merely because they express a true relation, that between absorption and abnormal dispersion. In the premises of these theories, the part that is true is the part common to all. It is the affirmation of this or that relation between certain things, which some call by one name and some by another. The kinetic theory of gases has given rise to many objections, to which it would be difficult to find an answer were it claimed that the theory is absolutely true. But all these objections do not alter the fact that it has been useful, particularly in revealing to us one true relation which would otherwise have remained profoundly hidden, the relation between gaseous and osmotic pressures. In this sense, then, it may be said to be true. When a physicist finds a contradiction between two theories which are equally dear to him, he sometimes says, "Let us not be troubled, but let us hold fast to the two ends of the chain, lest we lose the intermediate links." This argument of the embarrassed theologian would be ridiculous if we were to attribute to physical theories the interpretation given them by the man of the world. In case of contradiction, one of them at least should be considered false. But this is no longer the case if we only seek in them what should be sought. It is quite possible that they both express true relations, and that the contradictions only exist in the images we have formed to ourselves of reality. To those who feel that we are going too far in our limitations of the domain accessible to the scientist, I reply, these questions which we forbid you to investigate, and which you so regret, are not only insoluble, they are illusory and devoid of meaning. Such a philosopher claims that all physics can be explained by the mutual impact of atoms. If he simply means that the same relations obtain between physical phenomena as between the mutual impact of a large number of billiard balls, well and good. This is verifiable, and perhaps is true. But he means something more, and we think we understand him because we think we know what an impact is. Why? Simply because we have often watched a game of billiards. Are we to understand that God experiences the same sensations in the contemplation of his work that we do in watching a game of billiards? If it is not our intention to give his assertion this fantastic meaning, if we do not wish to give it the more restricted meaning I have already mentioned, which is the sound meaning, then it has no meaning at all. Hypotheses of this kind have therefore only a metaphorical sense. The scientist should no more banish them than a poet banishes metaphor, but he ought to know what they are worth. They may be useful to give satisfaction to the mind, and they will do no harm as long as they are only indifferent hypotheses. These considerations explain to us why certain theories that were thought to be abandoned and definitively condemned by experiment are suddenly revived from their ashes and begin a new life. It is because they express true relations, and had not ceased to do so when for some reason or other we felt it necessary to enunciate the same relations in another language. Their life had been latent, as it were. Barely 15 years ago, was there anything more ridiculous, more quaintly old-fashioned, than the fluids of Coulomb? And yet, here they are reappearing under the name of electrons. In what do these permanently electrified molecules differ from the electric molecules of Coulomb? It is true that in the electrons the electricity is supported by a very little matter. In other words, they have mass. Yet Coulomb did not deny mass to his fluids, or if he did, it was with reluctance. It would be rash to affirm that the belief in electrons will not also undergo an eclipse, but it was none the less curious to note this unexpected renaissance. But the most striking example is Carnot's principle. Carnot established it, starting from false hypotheses. When it was found that heat was indestructible and may be converted into work, his ideas were completely abandoned. Later, Clausius returned to them, and to him is due their definitive triumph. In its primitive form, Carnot's theory expressed in addition to true relations, other inexact relations, the debris of old ideas. But the presence of the latter did not alter the reality of the others. Clausius had only to separate them, just as one lops off dead branches. The result was the second fundamental law of thermodynamics. The relations were always the same, although they did not hold, at least to all appearance, between the same objects. This was sufficient for the principle to retain its value. Nor have the reasonings of Carnot perished on this account. They were applied to an imperfect conception of matter, but their form, that is, the essential part of them, remained correct. What I have just said throws some light at the same time on the role of general principles, such as those of the principle of least action or of the conservation of energy. These principles are of very great value. They were obtained in the search for what there was in common in the enunciation of numerous physical laws. They thus represent the quintessence of innumerable observations. However, from their very generality results a consequence to which I have called attention in Chapter 8, namely, that they are no longer capable of verification. As we cannot give a general definition of energy, the principle of the conservation of energy simply signifies that there is a something which remains constant. Whatever fresh notions of the world may be given us by future experiments, we are certain beforehand that there is something which remains constant, and which may be called energy. Does this mean that the principle has no meaning and vanishes into a tautology? Not at all. It means that the different things to which we give the name of energy are connected by a true relationship. It affirms between them a real relation. But then, if this principle has a meaning, it may be false. It may be that we have no right to extend indefinitely its applications, and yet it is certain beforehand to be verified in the strict sense of the word. How then shall we know when it has been extended as far as is legitimate? Simply when it ceases to be useful to us, that is, when we can no longer use it to predict correctly new phenomena. We shall be certain in such a case that the relation affirmed is no longer real, for otherwise it would be fruitful. Experiment without directly contradicting a new extension of the principle will nevertheless have condemned it. Physics and Mechanism. Most theorists have a constant predilection for explanations borrowed from physics, mechanics, or dynamics. Some would be satisfied if they could account for all phenomena by the motion of molecules attracting one another according to certain laws. Others are more exact. They would suppress attractions acting at a distance. Their molecules would follow rectilinear paths, from which they would only be deviated by impacts. Others again, such as Hertz, suppress the forces as well. But suppose their molecules subjected to geometrical connections analogous, for instance, to those of articulated systems. Thus they wish to educe dynamics to a kind of kinematics. In a word, they all wish to bend nature into a certain form, and unless they can do this they cannot be satisfied. Is nature flexible enough for this? We shall examine this question in Chapter 11(1), apropos of Maxwell's theory. Every time that the principles of least action and energy are satisfied, we shall see that not only is there always a mechanical explanation possible, but that there is an unlimited number of such explanations. By means of a well-known theorem due to Koenig's, it may be shown that we can explain everything in an unlimited number of ways, by connections after the manner of Hertz, or again, by central forces. No doubt it may be just as easily demonstrated that everything may be explained by simple impacts. For this, let us bear in mind that it is not enough to be content with the ordinary matter of which we are aware by means of our senses, and the movements of which we observe directly. We may conceive of ordinary matter as either composed of atoms, whose internal movements escape us, our senses being able to estimate only the displacement of the whole, or we may imagine one of those subtle fluids, which under the name of ether or other names, have from all time played so important a role in physical theories. Often we go further, and regard the ether as the only primitive, or even as the only true, matter. The more moderate consider ordinary matter to be condensed ether, and there is nothing startling in this conception. But others only reduce its importance still further, and see in matter nothing more than the geometrical locus of singularities in the ether. Lord Kelvin, for instance, holds what we call matter to be only the locus of those points at which the ether is animated by vortex motions. Riemann believes it to be the locus of those points at which the ether is constantly destroyed. To Weikert or Lamore, it is the locus of the points at which the ether has undergone a kind of torsion of a very particular kind. Taking any one of these points of view, I ask by what right do we apply to the ether the mechanical properties observed in ordinary matter, which is but false matter? The ancient fluids, caloric, electricity, etc., were abandoned when it was seen that heat is not indestructible. But they were also laid aside for another reason. In materializing them, their individuality was, so to speak, emphasized. Gaps were opened between them. And these gaps had to be filled in when the sentiment of the unity of nature became stronger, and when the intimate relations which connect all the parts were perceived. In multiplying the fluids, not only did the ancient physicists create unnecessary entities, but they destroyed real ties. It is not enough for a theory not to affirm false relations, it must not conceal true relations. Does our ether actually exist? We know the origin of our belief in the ether. If light takes several years to reach us from a distant star, it is no longer on the star, nor is it on the earth. It must be somewhere, and supported, so to speak, by some material agency. The same idea may be expressed in a more mathematical and more abstract form. What we know are the changes undergone by the material molecules. We see, for instance, that the photographic plate experiences the consequences of a phenomenon of which the incandescent mass of a star was the scene several years before. Now, in ordinary mechanics, the state of the system under consideration depends only on its state at the moment immediately preceding. The system therefore satisfies certain differential equations. On the other hand, if we did not believe in the ether, the state of the material universe would depend not only on the state immediately preceding, but also on much older states. The system would satisfy equations of finite differences. The ether was invented to escape this breaking down of the laws of general mechanics. Still, this would not only compel us to fill the interplanetary space with ether, but not to make it penetrate into the midst of material media. Fizeau's experiment goes further. By the interference of rays which have passed through the air or water in motion, it seems to show us two different media penetrating each other, and yet being displaced with respect to each other. The ether is all but in our grasp. Experiments can be conceived in which we come closer still to it. Assume that Newton's principle of the equality of action and reaction is not true if applied to matter alone, and that this can be proved. The geometrical sum of all the forces applied to all the molecules would no longer be zero. If we did not wish to change the whole of the science of mechanics, we should have to introduce the ether, in order that the action which matter apparently undergoes should be counterbalanced by the reaction of matter on something. Or again, suppose we discover that optical and electrical phenomena are influenced by the motion of the earth. It would follow that those phenomena might reveal to us not only the relative motion of material bodies, but also what would seem to be their absolute motion. Again, it would be necessary to have an ether in order that these so-called absolute movements should not be their displacements with respect to empty space, but with respect to something concrete. Will this ever be accomplished? I do not think so, and I shall explain why. And yet it is not absurd, for others have entertained this view. For instance, if the theory of Lorentz, of which I shall speak in more detail in Chapter 13, were true, Newton's principle would not apply to matter alone, and the difference would not be very far from being within reach of experiment. On the other hand, many experiments have been made on the influence of the motion of the earth. These results have always been negative. But if these experiments have been undertaken, it is because we have not been certain beforehand, and indeed, according to current theories, the compensation would be only approximate, and we might expect to find accurate methods giving positive results. I think that such a hope is illusory. It was none the less interesting to show that a success of this kind would, in a certain sense, open to us a new world. And now allow me to make a digression. I must explain why I do not believe, in spite of Lorentz, that more exact observations will ever make evident anything else but the relative displacements of material bodies. Experiments have been made that should have disclosed the terms of the first order. The results were nugatory. Could that have been by chance? No one has admitted this. A general explanation was sought, and Lorentz found it. He showed that the terms of the first order should cancel each other, but not the terms of the second order. Then more exact experiments were made, which were also negative. Neither could this be the result of chance. An explanation was necessary, and was forthcoming. They always are. Hypotheses are what we lack the least. But this is not enough. Who is there who does not think that this leaves to chance far too important a role? Would it not also be a chance that this singular concurrence should cause a certain circumstance to destroy the terms of the first order, and that a totally different but very opportune circumstance should cause those of the second order to vanish? No. The same explanation must be found for the two cases, and everything tends to show that this explanation would serve equally well for the terms of the higher order, and that the mutual destruction of these terms will be rigorous and absolute. The present state of physics. Two opposite tendencies may be distinguished in the history of the development of physics. On the one hand, new relations are continually being discovered between objects which seem destined to remain forever unconnected. Scattered facts cease to be strangers to each other, and tend to be marshaled into an imposing synthesis. The march of science is towards unity and simplicity. On the other hand, new phenomena are continually being revealed. It will be long before they can be assigned their place. Sometimes it may happen that to find them a place, a corner of the edifice must be demolished. In the same way, we are continually perceiving details ever more varied in the phenomena we know, where our crude senses used to be unable to detect any lack of unity. What we thought to be simple becomes complex, and the march of science seems towards diversity and complication. Here, then, are two opposing tendencies, each of which seems to triumph in turn. Which will win? If the first wins, science is possible, but nothing proves this a priori, and it may be that after unsuccessful efforts to bend nature to our ideal of unity in spite of herself, we shall be submerged by the ever-rising flood of our new riches, and compelled to renounce all idea of classification, to abandon our ideal, and to reduce science to the mere recording of innumerable recipes. In fact, we can give this question no answer, All that we can do is to observe the science of today and compare it with that of yesterday. No doubt after this examination we shall be in a position to offer a few conjectures. Half a century ago, hopes ran high indeed. The unity of force had just been revealed to us by the discovery of the conservation of energy and of its transformation. This discovery also showed that the phenomena of heat could be explained by molecular movements. Although the nature of these movements was not exactly known, no one doubted but that they would be ascertained before long. As for light, the work seemed entirely completed. So far as electricity was concerned, there was not so great an advance. Electricity had just annexed magnetism. This was a considerable and a definitive step towards unity. But how was electricity in its turn to be brought into the general unity? And how was it to be included in the general universal mechanism? No one had the slightest idea. As to the possibility of the inclusion, all were agreed. They had faith. Finally, as far as the molecular properties of material bodies are concerned, the inclusion seemed easier, but the details were very hazy. In a word, hopes were vast and strong, but vague. Today, what do we see? In the first place, a step in advance, immense progress. The relations between light and electricity are now known. The three domains of light, electricity, and magnetism, formerly separated, are now one, and this annexation seems definitive. Nevertheless, the conquest has caused us some sacrifices. Optical phenomena became particular cases in electric phenomena. As long as the former remained isolated, it was easy to explain them by movements which were thought to be known in all their details. That was easy enough. But any explanation to be accepted must now cover the whole domain of electricity. This cannot be done without difficulty. The most satisfactory theory is that of Lorentz. It is unquestionably the theory that best explains the known facts, the one that throws into relief the greatest number of known relations, the one in which we find most traces of definitive construction. That it still possesses a serious fault I have shown above. It is in contradiction with Newton's law that action and reaction are equal and opposite, or rather, this principle according to Lorentz cannot be applicable to matter alone. If it be true, it must take into account the action of the ether on matter, and the reaction of the matter on the ether. Now, in the new order, it is very likely that things do not happen in this way. However this may be, it is due to Lorentz that the results of Fizeau on the optics of moving bodies, the laws of normal and abnormal dispersion and of absorption, are connected with each other and with the other properties of the ether by bonds which no doubt will not be readily severed. Look at the ease with which the new Zeeman phenomena found its place, and even aided the classification of Faraday's magnetic rotation, which had defied all Maxwell's efforts. This facility proves that Lorentz's theory is not a mere artificial combination which must eventually find its solvent. It will probably have to be modified, but not destroyed. The only object of Lorentz was to include in a single whole all the optics and electrodynamics of moving bodies. He did not claim to give a mechanical explanation. Larmor goes further. Keeping the essential part of Lorentz's theory, he grafts upon it, so to speak, McCullough's ideas on the direction of the movement of the ether. McCullough held that the velocity of the ether is the same in magnitude and direction as the magnetic force. Ingenious as is this attempt, the fault in Lorentz's theory remains, and is even aggravated. According to Lorentz, we do not know what the movements of the ether are, and because we do not know this, we may suppose them to be movements compensating those of matter, and reaffirming that action and reaction are equal and opposite. According to Larmor, we know the movements of the ether, and we can prove that the compensation does not take place. If Larmor has failed, as in my opinion he has, does it necessarily follow that a mechanical explanation is impossible? Far from it. I said above that as long as a phenomenon obeys the two principles of energy and least action, so long it allows an unlimited number of mechanical explanations. And so with the phenomena of optics and electricity. But this is not enough. For a mechanical explanation to be good, it must be simple. To choose it from among all the explanations that are possible, there must be other reasons than the necessity of making a choice. Well, we have no theory as yet which will satisfy this condition and consequently be of any use. Are we then to complain? That would be to forget the end we seek, which is not the mechanism. The true and only aim is unity. We ought therefore to set some limits to our ambition. Let us not seek to formulate a mechanical explanation. Let us be content to show that we can always find one if we wish. In this we have succeeded. The principle of the conservation of energy has always been confirmed, and now it has a fellow in the principle of least action, stated in the form appropriate to physics. This has also been verified, at least as far as concerns the reversible phenomena that obey Lagrange's equations, in other words, which obey the most general laws of physics. The irreversible phenomena are much more difficult to bring into line, but they too are being coordinated and tend to come into unity. The light which illuminates them comes from Carnot's principle. For a long time thermodynamics was confined to the study of the dilatations of bodies and of their change of state. For some time past it has been growing bolder and has considerably extended its domain. We owe to it the theories of the voltaic cell and of their thermoelectric phenomena. There is not a corner in physics which it has not explored, and it has even attacked chemistry itself. The same laws hold good. Everywhere, disguised in some form or other, we find Carnot's principle. Everywhere also appears that eminently abstract concept of entropy, which is as universal as the concept of energy, and, like it, seems to conceal a reality. It seemed that radiant heat must escape, but recently that, too, has been brought under the same laws. In this way, fresh analogies are revealed which may be often pursued in detail. Electric resistance resembles the viscosity of fluids. Hysteresis would rather be like the friction of solids. In all cases, friction appears to be the type most imitated by the most diverse irreversible phenomena, and this relationship is real and profound. A strictly mechanical explanation of these phenomena has also been sought, but owing to their nature it is hardly likely that it will be found. To find it, it has been necessary to suppose that the irreversibility is but apparent, that the elementary phenomena are reversible and obey the known laws of dynamics. But the elements are extremely numerous, and become blended more and more, so that to our crude sight all appears to fetid towards uniformity, that is, all seems to progress in the same direction, and that without hope of return. The apparent irreversibility is therefore but an effect of the law of great numbers. Only a being of infinitely subtle senses, such as Maxwell's demon, could unravel this tangled skein and turn back the course of the universe. This conception, which is connected with the kinetic theory of gases, has cost great effort, and has not on the whole been fruitful. It may become so. This is not the place to examine if it leads to contradictions, and if it is in conformity with the true nature of things. Let us notice, however, the original ideas of M. Gui on the Brownian movement. According to this scientist, this singular movement does not obey Carnot's principle. The particles which it sets moving would be smaller than the meshes of that tightly drawn net. They would thus be ready to separate them, and thereby to set back the course of the universe. One can almost see Maxwell's demon at work. Footnote 1. Clerk Maxwell imagined some supernatural agency at work, sorting molecules in a gas of uniform temperature into A, those possessing kinetic energy above the average, and B, those possessing kinetic energy below the average. End of note. To resume, phenomena long known are gradually being better classified, but new phenomena come to claim their place, and most of them, like the Zeeman effect, find it at once. Then we have the cathode rays, the X-rays, uranium and radium rays, in fact a whole world of which none has suspected the existence. How many unexpected guests to find a place for! No one can yet predict the place they will occupy, but I do not believe they will destroy the general unity. I think that they will rather complete it. On the one hand, indeed, the new radiations seem to be connected with the phenomena of luminosity. Not only do they excite fluorescence, but they sometimes come into existence under the same conditions as that property. Neither are they unrelated to the cause which produces the electric spark under the action of ultraviolet light. Finally, and most important of all, it is believed that in all these phenomena there exist ions, animated, it is true, with velocities far greater than those of electrolytes. All this is very vague, but it will all become clearer. Phosphorescence and the action of light on the spark were regions rather isolated, and consequently somewhat neglected by investigators. It is to be hoped that a new path will now be made which will facilitate their communications with the rest of science. Not only do we discover new phenomena, but those we think we know are revealed in unlooked-for aspects. In the free ether the laws preserve their majestic simplicity, but matter properly so called seems more and more complex. All we can say of it is but approximate, and our formulae are constantly requiring new terms. But the ranks are unbroken. The relations that we have discovered between objects we thought simple still hold good between the same objects, when their complexity is recognized, and that alone is the important thing. Our equations become, it is true, more and more complicated, so as to embrace more closely the complexity of nature, but nothing is changed in the relations which enable these equations to be derived from each other. In a word, the form of these equations persists. Take for instance the laws of reflection. Fresnel established them by a simple and attractive theory which experiment seemed to confirm. Subsequently, more accurate researches have shown that this verification was but approximate. Traces of elliptic polarization were detected everywhere. But it is owing to the first approximation that the cause of these anomalies was found in the existence of a transition layer, and all the essentials of Fresnel's theory have remained. We cannot help reflecting that all these relations would never have been noted if there had been doubt in the first place as to the complexity of the objects they connect. Long ago it was said, if Tycho had had instruments 10 times as precise, we would never have had a Kepler, or a Newton, or astronomy. It is a misfortune for a science to be born too late, when the means of observation have become too perfect. That is what is happening at this moment with respect to physical chemistry. The founders are hampered in their general grasp by third and fourth decimal places. Happily, they are men of robust faith. As we get to know the principles of matter better, we see that continuity reigns. From the work of Andrews and van der Waals, we see how the transition from the liquid to the gaseous state is made, and that it is not abrupt. Similarly, there is no gap between liquid and solid states, and in the proceedings of a recent Congress we see memoirs on the rigidity of liquids side by side with papers on the flow of solids. With this tendency there is no doubt a loss of simplicity. Such and such an effect was represented by straight lines. It is now necessary to connect these lines by more or less complicated curves. On the other hand, unity is gained. Separate categories quieted, but did not satisfy the mind. Finally, a new domain, that of chemistry, has been invaded by the method of physics, and we see the birth of physical chemistry. It is still quite young, but already it has enabled us to connect such phenomena as electrolysis, osmosis, and the movement of ions. From this cursory exposition, what can we conclude? Taking all things into account, we have approached the realization of unity. This has not been done as quickly as was hoped 50 years ago, and the path predicted has not always been followed, but, on the whole, much ground has been gained. End of Chapter 10.